Problem 22.4 requires us to calculate electrical flux through a hemispherical shell. I like this problem because the calculations are not too strenuous, but it requires the knowledge of what electrical flux is and how it is exactly defined. So in start A, we are supposed to calculate the flux when electric field is as shown in the figure. The definition of electric flux through a surface is the product of E, the electric field, and the area, where the electric field has to be, or the component of the electric field has to be parallel to the area at the point. Or we can also say that it's the electric field and the area that we are considering has to be the projection to a surface that is perpendicular to the E. These both mean, just mathematically, that it's going to be EA, whereas cosine theta, and theta is the angle, if there is any, between the electric field vector and the normal of the area element. We can use any one of these forms, and depending on the situation, one of them is usually easier than the other ones. So I'm going to remove this one, and we'll use this formulation here. So it asks us to find the area element that is perpendicular to the flux lines. So if we think about, or field lines, so if you think about this field line, it will penetrate the shell somewhere here at the back. And the area element will look something like this. And its projection to the plane perpendicular to the electric field isn't the same shape. It's some kind of a square that is plotted here on this imaginary plane that caps off the hemispherical shell. So its projection would probably look something like this. Well, this is not a very good illustration, but the fact is that whatever the area is here in square centimeters or whatever, we are not interested in that area. We are interested in the area of its projection. So the area of this square is the A perpendicular that we are going to use in our calculations. And now we draw these little squares for all the field lines, and eventually they will fill up the whole perpendicular plane that encloses the sphere. So in fact, this would be dA, one of the infinitesimal area elements. So the actual A square that we are using in our calculations is going to be the area of this surface, which is only the area of a circle that has, if the radius is r, the area is pi r squared. So just to make clear, it's this flat imaginary disk. Therefore, the flux through the hemispherical shell becomes simply E times pi r squared. The part B asks what is the result if E is instead perpendicular to the axis. So here we have our shell. In this case, the E lines are coming from this direction. They will penetrate the shell and come out on the other side. Something like this. Now the definition is that any ingoing flux is negative because there the E vector and the area element vector are opposite. And so the angle between them is 180 degrees. So this comes to -1. So if we only evaluate the flux of these guys, we could write it would be minus E times A. But when these flux lines are coming out, over here the E and the A vector are parallel because we picked their parallel components. In this case, the cosine term turns out to be 1. So the EA is +1. This just illustrates the fact that any incoming flux is negative, outgoing flux is positive. Because the same field lines come in and go out through the surface, the total flux would be 0. Notice that in this case, the flux only exits the Gaussian surface or hemispherical surface. There is no surface at the entrance because this is a hemispherical cell. So it ventures inside the shell and only pierces through on the other side. So we only have the outgoing flux here, which is positive, as we can see from here.
Forgot the importance of being right. Don't sit there and act humble. I've heard your story 1,000 times. No trust.